EE World, I'm Martin Rowe. We are in New York City at the Brooklyn 6G Summit 2025 on the campus of the NYU Tandon School of Engineering. And we have some exhibits here, and this one is from Keysight.
Specific problem we were looking to address here is how to identify targets in a high clutter environment. So if you think of something like an indoor factory where you're looking at trying to track an autonomous vehicle, then there's going to be many targets in your returns, and you have to be able to try to find that. So clutter removal is one way of reducing the excess targets that you would see, but that may not be sufficient in some environments. So we developed an approach to use micro movements within an object to be able to identify this, and then developed an AI model to be able to track those different types of and identify those different types of targets.
Okay.
So in our demonstration we did last year, we showed that we could, using an OFDM radar system, that we could observe very small movements within an object. And what we did this year is we essentially extended that to say, okay, with real objects we're going to have a more complex vibration profile. You can think of like the robot, you have different motors moving, and there's going to be like a characteristic vibration profile from that. So we set out to see if we could identify those and then correctly classify those from the returns we get in the OFDM radar. So the system we were using was, again, using our OFDM emulation system, which consists of Keysight test instruments and software. We use a signal generator to create our OFDM signal. We're outputting that through an antenna, bouncing signals off of our target that's being stimulated by this multi-tone signal through a function generator and a vibration generator. We're receiving the targets with our UXR signal analyzer and doing the initial demodulation using our vector signal analyzer software, 89600, and then we've developed code in our test automation platform for doing the OFDM radar calculations. So these are the quick results of what we had. So we looked at multiple different various multi-tone stimulus patterns, and then you can see that we were able to achieve better than 90% detection rate of the correct target. So at this point I'm going to hand this over to my colleague Abhi, who's going to go through how we did this using our AI development platform.
Hi everyone, my name is Abhinav from Keysight. I am working in the AI labs of Keysight, and what I want to show you guys is our integrated AI development platform. So when Michael and I were looking at this problem last year, what we realized is that, and what was said in this conference, is that AI needs to be a scalpel, it cannot be a hammer. And how do we get to that point? And at Keysight, we develop our own machine learning algorithms, and we have this challenge as well. At which point do we use machine learning and which point do we use traditional DSP? To solve this problem, what we did is that we've developed an internal AI platform that helps us to generate data sets and test the data sets. It helps us retrain the models based on different types of data sets, and then it gives us some sort of transparent insights into AI decision making. And what this ultimately lets us do as Keysight is that it lets us analyze different types of models in different types of ways and helps us understand how the models are performing, both in context of the machine learning decisions that they're making, but also in context of the wider system and system-based analysis that we're doing. So what I'm going to show here is a very simple OFDM radar signal processing setup. Here, what you can see is that as you go through the multiple DSP processes, you extract different types of information. And the important thing here is to understand when to apply machine learning. And just as I spoke about earlier, where I talked about that scalpel and the hammer, what we did in the beginning is that we threw the hammer at this problem, where we used the machine learning algorithms all the way at the very beginning. That yielded minimal accuracy, however, we knew it could be better. The model was bloated, it was a little bit too slow, and we wanted to have higher accuracy and lower latency. So we moved the machine learning algorithm further and further down the DSP line, where we optimized it to perform better and also optimized it to be lighter. And what this allows us to do through our platform is we were able to track the model through its development, understand why the decisions were being made, and ultimately be able to come up with a model that was high in accuracy and low in latency.